So thank you very much for your kind introduction. So as John mentioned in the introduction, I had the great privilege of being Andrew Wiles' postdoc in Princeton in the time when the proof of Fermat was announced. And I remember the months and even the year after that announcement when everyone was scrambling to catch up and understand the ideas that have been introduced as among the most exciting of my mathematical life. So it's a pleasure to be here to take part in the celebration of Andrew Wiles' achievements. So the title of my lecture, Andrew Wiles' Marvelous Proof, is a reference to the famous annotation of Fermat in the margin of his copy of Diophantus, where after writing down what was later to be known as Fermat's last theorem, he wrote, I have discovered a truly marvelous proof of this, which the margin is too small to contain. So, of course, we will never know what Fermat's marvelous proof was. There are even questions about whether this proof actually existed. On the other hand, we've had the privilege of knowing Andrew Wiles' marvelous proof. It's been now in the public domain for over 20 years, and it's had a remarkable impact on number theory and mathematics. And so I want to talk a little bit about the impact it's had. So what are the goals of my lecture? So after I was approached by the Abel committee to give this lecture, I was told that my mission, should I choose to accept it, would be to explain to an audience of non-experts, and maybe with an undergraduate background in mathematics, what are some of the important ideas in Wiles' proof and the reason why they've had such an impact. Okay? So maybe this is mission impossible, I don't know. So in my lecture, in fact, I'm going to say almost nothing about Fermat's last theorem, but rather I will focus solely on the modularity conjecture, which was also, of course, one of the themes in Andrew's lecture before. And so I want to give you first a feeling for the statement of the modularity conjecture. But even more, I want to convey some of the ideas in the proof that have had later on a tremendous impact on the subject and sort of present the larger context in which this proof fits in. So this is my goal for my talk. So let me begin by reminding you, or telling you, I guess, some of the reasons why this modularity theorem of Wiles is so important. So, of course, the first one is that the most well-known is that it applies Fermat's last theorem. This is what had, of course, the greatest public impact. It was featured on the front page of the New York Times, a rather large spread that came out in the days following Andrew's announcement. And it led to the publication of some very popular books, like the one of Simon Singh, which you'll be hearing about more, I guess, in the afternoon's lecture. The second reason is that it's a crucial central statement in the theory of elliptic curves. And the theory of elliptic curves is itself a very important part of number theory today. And this is something that's going to be discussed in more detail in Manjul Bhargava's lecture, the first lecture this afternoon. But the third reason, and this is also conveyed a little bit in Andrew's lecture before, is that this modularity conjecture for elliptic curves is actually a small part of a much larger picture concerned with understanding non-abelian extensions of the rationals. This picture was elaborated by a number of mathematicians, among them Shimura and Langlands, and has since then become known as the Langlands Program. And this is the aspect I want to focus on, the role of, the place of Andrew Wiles' work within the larger framework of the Langlands Program and the remarkable progress that it's led to in this program. Okay, so the Langlands Program has often been called one of the grand unifying theories or visions in mathematics and number theory in particular. Roughly speaking, it's a kind of it connects questions of number theory, questions about whole numbers, Diophantine equations, with mathematical structures that a priori seem completely unrelated, having to do with analysis, with continuous transformation groups of the kind that were, for example, studied by Sophus Lie, another great Norwegian mathematician. so this graphic is meant to kind of convey this kind of connection, but now I want to say a little bit more, try to kind of be a bit more precise about what the nature of this program is and what it does. So I want to give a kind of beginner's guide to the Langlands program without assuming any prior background, so at least to give you a feeling for the kind of questions that the Langlands program tries to understand. So I'm going to begin with objects that are the mainstay of number theory, namely Diophantine equations. So a Diophantine equation is simply a polynomial in a certain number of variables with integer coefficients. Okay, so something like this. And one could also, if one wanted to be a little bit more general, consider systems of polynomials, but I'm not going to do that. For me, one polynomial is quite enough for the examples I'll consider. So some very classical examples of Diophantine equations are the, of course, Fermat's equation, which is one of the main themes of this week, I guess. Another example is which is also very well studied and celebrated, the so-called Brahmagupta-Pell equation that was studied first by the Indian mathematician Brahmagupta in the 7th century. So it's equation x squared minus dy squared equals 1, where x and y are the variables, and d is kind of a parameter of the equation. And finally, the third class of equations, which is also very important for our study, are the elliptic curves, the cubic equations in two variables, x and y, where here a and b are parameters of the equation, which could be integers or might also be rational numbers. Okay, so what makes this study Diophantine, what do we call these Diophantine equations, is that we're interested in the set of solutions to the equation with either integer values or if sometimes, as the case may be, rational coordinates. So we're interested in these sets x of z, x of z of integer solutions or x of q of rational solutions. Okay, so one of the insights, which at first seems rather simple-minded, but turns out to be remarkably profound in the study of Diophantine equations, is that one can gain a lot of handle on the equation, say if you want to understand the integer solutions, by trying to understand first the equation over simpler number systems. And in algebra, one of the simplest number systems, simpler than the integers or the rational numbers or certainly than the real numbers, are the set of residues modulo a given integer n, which already made an appearance in Andrew's lecture before. So the set of integers from 0 to n minus 1, equipped with the usual arithmetic operations of addition, subtraction, and multiplication, but where every time you take the remainder after division by n to stay within this set. So this is a set of so-called residue classes modulo n. It's sometimes called also the residue ring modulo n. And so it's equipped with all these natural arithmetic operations, addition, subtraction, and multiplication. And it's particularly simple since, for example, it's a finite set. And in fact, if the modulus n is a prime number, then this algebraic structure is even nicer. It's what's called a field. It's endowed with an extra arithmetic operation of division. Namely, every element has a multiplicative inverse, an inverse under multiplication. So you can, within this algebraic structure, which seems a priori very simple, you can even perform division by non-zero elements. And in fact, this fact that the residue ring modulo p is a field, has a division, is a property that characterizes the prime numbers among all integers. And in fact, it's a very, very valuable algebraic characterization of the primes, which underlies, for example, many primality tests. And Évariste Galois, who also has appeared in the previous lecture, and I'm sure in a number of other discussions today, also observed, I mean, one of his big contributions beyond the Galois theory, which he's famous for, was to see that for every prime power, every power of a prime, there is, in fact, a field, a finite field of that cardinality. So a structure in which the four basic arithmetic operations are defined, and in which you can sort of therefore do algebra and arithmetic. And in fact, this field with p to the r elements is even unique up to the isomorphism of structures. Okay, so if we have one of these finite fields, well, we can consider the set of solutions of the equation, so if we have now our x, which is a polynomial equation. So some polynomial, well, the coefficients of the polynomial are integers. But an integer can be viewed as an element of this finite field by taking the corresponding residue class. And therefore, we can consider the set of all values of x1 up to xn in this finite field which satisfy the equation. So this solution set is, of course, a finite set, since x1 up to xn are ranging over fp to the r. And therefore, well, the most basic invariant we can associate to this set is its cardinality, which I will call n sub p to the r. So in this way, we obtain an arithmetic sequence, np, np squared, etc., which is indexed by the powers of a fixed prime p. And there's one question we could ask is, how does this sequence behave? Does it satisfy any nice patterns? What patterns are satisfied by this sequence? Now, a typical gambit when you're trying to understand the sequence in arithmetic or combinatorics or many other parts of mathematics is to try to package this sequence in a generating series. So the most naive thing to do would be to consider the sum of np to the r times t to the r, so the infinite power series like that, where t is just a formal variable, and see what you can say about this series. For technical reasons, it turns out to be better to consider this kind of modified series where you divide the rth term by the integer r, and in fact even to exponentiate it, to apply the exponential, which gives you another formal power series in the variable t. Okay, this power series is not completely obvious from the definition I gave here. It turns out to have actually integer coefficients. Okay, this is what leads us to the zeta function of the equation x associated to a fixed prime p. And these zeta functions were somehow implicit already, I think, in the work of Gauss, maybe even before that. And they were first formally defined by Artin and Hasse at the beginning of the 20th century. Okay, so it turns out we know a lot about these zeta functions. They have many beautiful, remarkable properties. So the first fundamental result we have about them is that they're actually rational functions in T. The zeta function is actually a ratio of polynomials, P and Q, in the variable T. So that's the first, which was proved by Wey, Dwork. The second thing we know, and this is a remarkable insight which was introduced first by Wey and was part of what are called the Wey conjectures, is that the degrees of this numerator and denominator that occur in the zeta function are determined by the shape of the complex solutions of the equation. So this is a remarkable interaction between, so these counting functions, which a priori are formed by counting solutions of the equation modulo various, in various finite fields of p power cardinality, and that somehow connects with the topology of the complex solutions. This is the first indication of these deep principles of kind of resonance between the behaviors of the equation over different fields. And the third fact we know about is that the roots of the zeta function, the reciprocal roots, are complex numbers of some given absolute value. This last fact is very important. It's what's called the Riemann hypothesis for the zeta function, and is one of the things that earned Deligne his Abel Prize some years ago. So here's the motivating question for the Langlands program that I wanted to get to, and that's simply the question that arises if you try to understand the function which to a prime p associates this number np, this counting function, or if you want to be a little bit more ambitious, the function which to p associates the zeta function. So how does the zeta function of an equation vary as a function of the prime p? And so this is the question. We will see in McGill's lecture, actually, that the study of this independence of this function leads to deep insights about the behavior of the equation over the integers of the rational numbers. That's the first thing. And as a way, keeping in line with this philosophy of packaging the arithmetic information into a generating series, we can define the zeta function of the Diophantine equation over the integers by taking a product over all the primes of these zeta functions. But now, we don't want to just take the product of zeta of t, because that might have convergence issues, but rather we plug in p to the minus s in the zeta function at p, and then take the infinite product and hope that that converges somewhere, which it always does. So here, s you can think of as an integer variable, and it's a fact that this infinite product converges once s is large enough. Okay. So let me begin with the simplest kind of equations that could arise, the equation x equals 0. Well, in that case, it's very easy to solve over any field whatsoever. The number of solutions is always 1. So this is the equation for a point, if you think of it in algebraic geometry terms. And therefore, the number np to the r is always equal to 1. So that means that if you look at the zeta function, okay, there's a typo here, this shouldn't be there. You just get the sum of t to the r over r, which is this simple rational function, 1 minus t inverse. And then the infinite product over all the primes of this, you recognize in this expression, the infinite product expression for the Riemann zeta function. And indeed, what you get at the end is just the famous Riemann zeta function. So you can already see that for the simplest conceivable Diophantine equation, the zeta function is already a very interesting object, which with many, of course, many interesting questions about it. So let's move on to the next interesting case, the case of quadratic equations in one variable. So as you all learned in grade school, when you study quadratic equation, the basic invariant that governs the behavior of the equation is the discriminant, b squared minus 4ac. And you know that the equation has 2 roots when the discriminant is a non-zero square, and 0 roots if the discriminant is a non-square. And that fact is true algebraically over any field. And so we know we see that, therefore, this number, np, of the equation is either 0 or 2, depending on this property of the discriminant. So we can ask, is there a simple formula for this quantity np as the prime p varies? When you first see this recipe, it doesn't seem apparent that it's going to be a simple recipe because, well, you know, checking that delta is a square or not square mod p, you would have to maybe, if you were at your most naive, run through all the quadratic residues or non-residues modulo p. I mean, so look at all the squares and see whether your delta is in this list or not. And if p is very large, then this could take a long time. So it looks a priori like a rather subtle condition on the prime p. So let's look at an example. So here's the example, x squared minus x minus 1. For this equation, the discriminant is 5. The root of this equation is the celebrated golden ratio. And you can count these np, and then when you do that, so you can do it on a computer if you want, just do it experimentally, you find that there are actually 2 distinct roots when p is a prime, different from 5 among this list of primes. These are the first few primes where you have 2 roots. And here are the first few primes where you have 0 roots. So you can see that it's sort of 2 or 0 equally often, roughly. And then you can try to detect patterns, see when it is. And if you stare at this list, it won't take you very long to realize that the answer, whether there are 2 or 0 roots, seems to depend only on the last digit of the prime. So if the last digit is 1 or 9, then there are 2 roots. And if the last digit is 3 or 7, there seem to be no roots. So that's what it seems to be. So it really only seems to depend only on what the prime is modulo 10. So now, of course, your understanding of this function is dramatically improved. In order to understand this np, you only need to look at the last digit of your prime. Okay, so that's based on this evidence, you might make this educated guess that np is 2, precisely when p is 1 or 4 modulo 5, in fact. It really only depends on the prime modulo 5, and it's 0 if p is 2 or 3. And in fact, this guess is right, and it's general. It's a part of a more general phenomenon, which is one of the most important consequences of quadratic reciprocity. So the fact is that for any quadratic equation in one variable, with a certain discriminant delta, then the function which to p associates np is actually a periodic function. So of period length 4 delta. So to understand this function np, you only need to know the first few values up to delta or 4 delta, I don't know, and then you know the function forever. Okay, so that has, of course, an impact on our understanding of the zeta function of the equation. So for example, for this original equation, x squared minus x minus 1, the zeta function has this very simple shape. So it's the Riemann zeta function times another factor. And this other factor is a sum of reciprocals of powers of all the integers that are prime to 5 with a pattern. So it and it repeats with period length 4 with a pattern of signs plus, minus, minus, plus, etc. So it has this very simple shape, and of course having this simple shape allows us to make some analysis of the zeta function. So these right-hand examples these are kind of generalizations of the Riemann zeta function. They are called Dirichlet L series or Dirichlet L functions, and they're somehow, in some sense, the simplest generalization of the zeta function. And so one can say, therefore, because of this, because of quadratic reciprocity, essentially, that the zeta function of quadratic equations are well understood analytically. Okay. It turns out that a similar thing is true for quadratic equations in more than one variable. So the same pattern persists. So it's a general fact that the zeta function of a completely general quadratic equation in variables can be broken up into factors that involve only these basic constituents, the zeta function or the more general Dirichlet L functions. Okay, so it's sort of how the same behavior is in the one variable case, and that means that in some sense quadratic Diophantine equations are well understood, at least from the point of view of their zeta functions. There are maybe other questions that are more subtle, but from this point of view, we have a good handle on quadratic equations. So that means that things will become more interesting when we begin to consider equations of higher degree. Okay. So let's move on to cubic equations. We'll start with cubic equations in one variable. So here's an example which looks a bit similar to the one we had before. I now consider the equation x cubed minus x minus 1. Okay? So that has discriminant minus 23. You can compute the discriminant, and it turns out to be minus 23. And, provided the prime doesn't divide 23, then this polynomial will have distinct roots, and it will have either 0, 1, or 3 roots over the field with p elements. So NP could be either 0, 1, or 3, and we'd like to know what kind of pattern would be satisfied with this NP. So this is a theorem that was proved by Hecke, I think, in this case. So for all primes, different from 23, for 23 there are multiple roots, so we're going to ignore that case. So the first scenario is if p is not a square modulo 23. And if p is not a square modulo 23, then there's always a single root over that field. So that's a criterion that looks like what we had before, the quadratic equation governed somehow by quadratic reciprocity. The interesting novelty is what happens when p is a square modulo 23. And in that case, there are two possible scenarios. NP is either 0 or 3. And which it is depends on whether p can be represented as the value of a certain binary quadratic form. So these two binary quadratic forms, 2a squared plus ab plus 3b squared and a squared plus ab plus 6b squared, are quadratic forms of discriminant minus 23. So you see this minus 23 appearing again here. And this is a kind of an arithmetic characterization of how this cubic polynomial factors modulo p in terms of the representability of the prime as the value of a certain binary quadratic form. So this means that the problem, again, is endowed with a certain arithmetic structure. And, Hecke's theorem can be used to say something about the zeta function of the equation. So I can write the zeta x cubed minus x minus 1 as the zeta function times the remaining series, which is the interesting part, the sum of a n to the minus s. So this is going to be some kind of Dirichlet series, some kind of linear combination of reciprocals of powers of n. And the coefficients a n that arise here, I'm going to package them in a slightly different way as a generating series of a variable q. This is something which is common to do in the theory, so we try to understand the sequence of ANs in the zeta function of the cubic equation by packaging into what's called a q series sometimes. And this q series satisfies many striking patterns. The first is this formula here, which is just a restatement of Hecke's theorem. So from this you can derive Hecke's theorem that so what is this AP is closely related to NP, etc. And it depends on whether P arises as a value of this quadratic form or that one. And it also has this very striking infinite product expansion. So this is a really remarkable identity of formal power series. I would challenge you, I mean, this is something you can go on a computer and you can test, you can see that this identity is true however far you want. I would put you to a challenge to try to prove that directly from just first principles. The fact that such beautiful and striking patterns emerge is the reflection of a much deeper theory. And this is sort of part of the general, well, one of the many wondrous identities that arise from the theory of modular forms. And so this is how modular forms first make an appearance in our discussion. So in fact, the fact is that if you replace the q, this formal variable q, by e to the 2 pi I z, so as we had in Andrew's lecture, so that makes the series automatically periodic of period 1. And this series turns out to be the prototypical example of a modular form. So it satisfies this kind of transformation property where you have a sort of an invariance under 2x2 matrices and SL2Z, which are upper triangular modulo 23. 23 was our discriminant that we had before. And the only difference with the transformation property that came up in Andrew's lecture before is that in this automorphy factor, this transformation factor here, we have a 1 instead of a 2. So this is an example of what's called a modular form of weight 1 and level 23. And in fact, Hecke proved that similar properties are satisfied by the zeta functions of arbitrary cubic polynomials in one, or cubic equations in one variable. This is a completely general phenomenon for equations of degree 3. Now, modular forms appear in many guises in number theory, and I sort of wanted to mention this famous quote of Martin Eichler, who was one of the mathematicians very active in this field in its early days. He said that there are 5 elementary arithmetical operations: addition, subtraction, multiplication, division, and modular forms. And I think I first heard this quote actually in Simon Singh's documentary about the proof of Fermat. So now let's move on. Okay, so I said something about cubic equations in one variable. What happens with cubic equations in 2 variables? So we look at an equation like, well, any cubic equation in 2 variables, provided it already has one rational solution, so we'll assume that now, can always be brought into the following very simple form. Y squared equals x cubed plus ax plus b. So it's an equation of an elliptic curve in this sort of what's called the short Weierstrass form. So essentially, we lose no generality by considering cubic equations of that type, or closely related. And so here's an example. We could consider the equation y plus 1 equals x cubed, which is actually not quite of that type, but almost. And we can compute its zeta function. So like as before, as with the cubic equation in one variable, the zeta function of our elliptic curve factors as something kind of simple and well understood, which is essentially a shift of the Riemann zeta function, times a more mysterious piece, which remains. So it's a Dirichlet series where with integer coefficients, these ANs are integers, and we would like to understand the patterns satisfying the coefficients in the zeta function. And again, we package them into a Q series like this. I write f of q as this linear combination. And the first few coefficients look like that. So this is sort of to underscore the fact that they really are integers. The expansion is kind of interesting. It looks a bit sparse. I mean, there are many coefficients that are 0, and the coefficients that are non-zero seem to grow a little bit, but not too much, but more than the coefficients we had before for the cubic equation in one variable, which is to be expected since now we have more solutions, even though we have 2 variables. And it turns out again that like the Q series we had before, this one satisfies a very remarkable factorization formula of this sort. So there's a very nice identity. And in fact, this generating series is again a modular form. So this is a simple special case, concrete special case, of the general theorem that Wiles proved, the modularity theorem for elliptic curves. So it asserts that this generating series, as we saw in the previous lecture, transforms nicely under matrices which are now this time upper triangular modulo 27, and the transformation factor involves now a square of the denominator of the fractional linear transformation. Okay, so this is what is this was what it was known before Wiles as the Shimura-Taniyama conjecture or Shimura-Taniyama-Weil conjecture. So if E is any cubic equation in two variables, then this pattern persists. The zeta function is of this form, where what's left over, the Dirichlet series that's left over, this one here, is the Dirichlet series attached to a modular form of weight 2 in a certain level. More precisely, okay, so yeah, that's the thing, and that was exactly what Wiles proved. So Wiles showed that if E is any semi-stable elliptic curve, then E satisfies the Shimura-Taniyama conjecture. And this is a picture of, I think, the announcement, the last lecture in Cambridge where this result was announced. More precisely, again, we have this kind of transformation behavior under matrices which are upper triangular modulo an integer n, the same integer n that occurred in Andrew's lecture before. This is something that's called the level of the modular form, and it can be computed independently as the conductor of the elliptic curve. It's what's called the arithmetic conductor of E, and it can be effectively calculated in terms of the equation of the elliptic curve by an algorithm of Tate. And the semi-stable curve, so there's this condition of semi-stability that occurs in the original modularity theorem of Wiles. This condition can be phrased concretely as the condition that the conductor is square-free, is not divisible by the square of any prime number. Well, anyway, the condition of semi-stability was later removed by further refinements of the technique due to Breuil, Conrad, Diamond, and Taylor. So now we have the modularity theorem for all elliptic curves over the rational numbers. Okay, so how does this modularity fit into the more general framework of the Langlands program? So a Diophantine equation is said to be modular if its zeta function can be expressed in terms of generating series attached to modular forms in some very general sense. So the actual buzzword for that is, these are sometimes referred to as automorphic representations, and they also made a very brief appearance in Andrew's lecture. I'll say very little about them, but there's this sort of very, well, all I want to convey is that there's this very general notion, generalization of an object of which modular forms are in some sense the simplest concrete instance. And the main conjecture of the Langlands program is that in this generalized sense, all Diophantine equations that occur are modular. Their zeta functions can be understood via a connection with some kind of modular form or automorphic representation. And this fundamental problem of the Langlands program is really, it can be viewed, of course, as a vast generalization of quadratic reciprocity, which underlies the calculation of the zeta function of a quadratic equation. And it sort of course, underlies these non-abelian reciprocity laws, or the study of non-abelian extensions, which Andrew was referring to in his lecture. It was one of the main themes of his lecture. So what was known about modularity of Diophantine equations before the work of Andrew Wiles? Well, we knew that quadratic equations are modular. That's quadratic reciprocity, as I explained. Then the work of Hecke and Maas somehow led to the understanding that all cubic equations in one variable are modular. They're associated with some kind of modular form, either a form of weight 1 or something called the mass form. And then there is this wonderful theorem of Langlands tunnel, which plays a very important role in Andrew's proof, as also was explained in the previous talk, that quartic equations in one variable are also modular. So equations of degree 4 are modular as well. And the fact that these cubic and quartic equations can be handled, can improve the modularity, is really, what underlies that is the fact that these equations can be solved by radicals. So the very same fact that allowed the Italian algebraists of the Renaissance to solve the equations by radical are what allows us to prove the modularity. And they're symmetry groups in part. The reason, from the point of view of Galois theory, if you want, is that the symmetry groups underlying these equations are the symmetry group on 3 and 4 letters, which have this property of being solvable, which means that they're not too far, in a sense, from being abelian. They can be kind of broken up into abelian constituents, and that's what makes these equations more tractable from the point of view of modularity. And, well, prior to this work of Wiles, modularity was only known for finitely many elliptic curves over Q. So there were really no serious examples of equations in more than one variable for which modularity was known. And the way that it was proved for these finitely many elliptic curves up to isomorphism was by essentially almost verification. I mean, there was no general technique for getting the modularity. So why is the modularity of elliptic curves important? Let me return to that question, which I also raised at the beginning of my talk. Well, so, of course, this theorem confirms the Langlands conjecture in an important new case, namely the case of elliptic curves. But you could still say, well, among all Diophantine equations that could arise, elliptic curves are still one very special instance, and what does it tell us about the broader picture? Well, still, elliptic curves have a really special place in number theory, even though they might seem, especially to someone with algebraic geometry sensibilities, as a very, very special kind of equation. They're extremely rich in number theory, and a lot of very deep number theory has been done entirely around the theme of elliptic curves. And this is something that you'll hear more about in McGill's lecture this afternoon. And they also have had many applications and things like cryptography. And so they're really a wonderful structure for number theory. One point is that the modularity sort of plays an essential role in the actual formulation, the very formulation of the BSD conjecture, which is something that McGill will talk about more. So another point that I want to make, and this is what I'm going to focus on for the remainder of my lecture, is that Wiles' proof leads to a revolutionary new approach to understanding modularity in much more general settings. And I want to sort of focus on the ingredient or the element in Wiles' proof that somehow gives us a purchase on making much more further progress on the Langlands program and on modularity results. And to explain this point, I really have to discuss Galois representations, which were also an object that came up in Andrew's talk before. So a Galois representation, in general, is a homomorphism from the absolute Galois group of Q. So this is the automorphism group of the field generated by all algebraic numbers. This group is very large. So for technical reasons, it's good to restrict to a certain quotient, which I will call GQS, which consists, in some sense, of algebraic numbers that have good reduction outside a finite set of primes. S is going to be a finite set of primes, and so we only look at algebraic numbers that are good outside of that finite set. And we look at homomorphism, so we look at quotients of this group that can be realized as subgroups of the general linear group, the group of n by n invertible matrices, with entries in a field L. And this group now is, in red, I put the slightly more technical parts of the lecture, things that you don't really have to understand. If you don't need to know the definition, don't worry too much. So we look at some kind of sub-extension of the full set of algebraic numbers, okay? And L is a field which is endowed with some kind of topology, which allows us to talk about continuous homomorphisms. And the main examples for our discussion are going to be the field of real or complex numbers, the finite fields of cardinality L to the R, where L is a prime, and the subfields are what are called the L-adic numbers. Okay, there's a typo here. This should be an L. Okay. Okay, Galois representations are really an absolutely crucial object of number theory. Many famous number theorists have made contributions to the study of Galois representations, including, in fact, 3 former Abel Prize winners before Andrew Wiles. So here, in fact, here you have a picture of Jean-Pierre Serre, and the NP that appears in the lecture that he's giving is exactly the same NP as in my lecture. So it's the sort of counting points for some equation. So Serre, Tate, and Deligne have all really made fundamental. So based on the record, in fact, you could conclude that if you're a number theorist and you want to win an Abel Prize, then you really should work on Galois representations. Okay, so, well, to a Galois representation, we can associate a zeta function in much the same way that it was done for the Diophantine equations before. So this group, GQS, this Galois group of the algebraic numbers, contains a distinguished element for each prime P, which is different from S. And this is that's called the Frobenius element at P, that was mentioned also in Andrew's talk. And this Frobenius is going to be denoted sigma p, actually, much as in the previous talk. So from this, we get an arithmetic sequence that we can associate to any Galois representation. If we have a representation rho, we can take the image of the rth power of the Frobenius at P. Now, this is a matrix which is well defined up to conjugation because the Frobenius is only defined up to conjugacy. But then the trace is a completely well-defined numerical invariant. And this number is what we call n sub p to the r. And now we package these n sub p to the r's in exactly the same way as we did for Diophantine equations, and we get then a zeta function associated to the Galois representation. And one of the most, I think, important insights in the number theory in the 20th century, largely, was the understanding that the two classes of zeta functions, the zeta functions of Diophantine equations and the zeta functions of Galois representations, are intimately related. And that if X is any Diophantine equation, we can find a collection, and you can find two Galois representations, in fact, for which the zeta function of the equation can be written as a ratio of the zeta function of these two Galois representations. But Galois representations have this extra feature that, I mean, when you're looking at representations of a group, it's natural to single out the ones that are irreducible, that represent in some sense the atomic constituents, the irreducible pieces of a general representation. And so you can more generally express the zeta function of a Diophantine equation as a product of zetas associated to irreducible Galois representations with eventually some integer exponents. So you always have such an expansion. And in some sense, the zeta functions of the Galois representations are more fundamental objects. They reveal, you can view them as somehow the atomic irreducible constituents of the underlying zeta function or of the underlying Diophantine equation, and they sort of reveal hidden structure in the underlying equation, which wouldn't be apparent when you first look at it. So that's and a lot of the work on proving modularity is, of course, in the language of Galois representations. So now we can rephrase the Langlands program by saying that a Galois representation is modular if its zeta function can be expressed in terms of modular forms, a very natural generalization, of course. And the fundamental problem of the Langlands program now can be reformulated as the goal now is to show that all Galois representations, eventually with some technical restrictions that somehow promise that they would come from Diophantine equations, are associated to modular forms or to automorphic representations. So this is the somehow more modern view of looking at the Langlands program. And so we can look at, so one of the things that we gain by doing this is that if we have now a representation with values in the elliptic integers. So ZL is the inverse limit of Z mod L to the n. So we saw Galois representations values in Z mod L to the n in the previous talk, and you can kind of package them together to get these so-called elliptic Galois representations. And when you have such a thing, you can consider its mod L reduction, which is a simpler thing. It has a finite image in particular. And this operation of reduction modulo L would seem very contrived from the point of view of the NP of a Diophantine equation. So you take a Diophantine equation, you count its solutions over finite fields of cardinality P, and then you take this resulting number, you reduce modulo L. What does that mean? That seems like a very artificial thing to do. From the point of view of Galois representation, this is completely natural, because you have this natural homomorphism from GLN-ZL to GLN-FL. Okay. Now I can state a result which is somewhat more technical than the modularity theorem of Wiles, but in some sense is really the heart of Andrew Wiles' proof, and it is the statement that has led to a fantastic number of generalizations and fantastic progress in the Langlands program. And this is the so-called modularity lifting theorem. The modularity lifting theorem asserts that if you start with a Galois representation into GL2ZL, which satisfies some technical conditions and needed to ensure somehow that one can do things, then if the mod L reduction is modular, then so is the representation rho. So what Wiles, and this type of result, at the time when it was introduced by Wiles, was completely stunning and completely new. No one had ever seen a statement of this kind. Since those days, these kind of modularity lifting theorems have proliferated. There have been dozens, hundreds maybe, of generalizations of this modularity theorem with weaker and weaker conditions or working in more and more general cases. And these modularity theorems are the ones that have led to fantastic. So this is kind of a wonderful template, a paradigm for making further progress on the Langlands program. This has really generated a whole industry and led to a lot of advances, as I said just before. And before I say anything about the new progress in the Langlands program that kind of arose from this modularity lifting theorem or its generalizations, let me explain to you how this can be used to prove the modularity of elliptic curves. Okay, that's Wiles' proof of the modularity. So we start with an elliptic curve, and you consider the associated mod 3 representation, whose image is a subgroup of GL2 of the field with 3 elements. And we can then consider the corresponding triadic representation, which has values in a much bigger group. And to prove the modularity of the elliptic curve, all we need to do is to show that this representation rho is modular, since the zeta function of rho is essentially the zeta function of the elliptic curve. Okay, so we start with this result of Langlands tunnel, which tells us that rho bar is modular. And the reason why we know that rho bar is modular is that this happy circumstance, as Andrew also explained in his talk, that the target group GL2F3, modulo the center, is isomorphic to the symmetric group on 4 letters. So the 3 torsion points on an elliptic curve have the modularity property for exactly the same reason that the quadratic equation is solvable, because they have the same underlying group of symmetries. I think it's actually a wonderful example of continuity in mathematical ideas. The reason why the Italian algebraists of the Renaissance were able to solve the quadratic equation by radicals is the same reason why Langlands tunnel were able to prove the modularity of all quadratic equations, and that's the same reason why Wiles was able to prove the modularity of sufficiently many triadic Galois representations to get the modularity of all elliptic curves over the rationals. Okay, so from this we know if the mod 3 representation is modular, and if E is semi-stable, it turns out that the technical conditions in the original modularity lifting theorem of Wiles are satisfied, more or less, and then one concludes, using Wiles' modularity lifting theorem, that the representation rho is modular, and therefore so is E. This is a slightly oversimplified account of the proof. There are some extra complications that arose on the way, but it's sort of a conceptual account. Okay, so the principle that's really important in the modularity lifting theorem of Wiles is this principle that modularity is in some sense contagious, that in many situations one can hope that it will be transmitted from the mod L representation to the corresponding elliptic representation. And so that's really, I think, what the main thing that accounts for the tremendous impact that Wiles' ideas have had over the last 2 decades, and sort of why these results have opened a new era in number theory, as in the words of the Abel Prize citation. And indeed, since 1994, when Wiles' proof was published, the subject has really had a real golden age of of progress in which many open problems that before then seemed completely out of reach gradually succumbed to the same kind of techniques that had been used to prove the modularity of elliptic curves. And so let me now just finish my talk by quickly telling you a few of these examples of these results. So, for example, the two-dimensional Artin conjecture. This concerns Galois representations with values in GL2C. An Artin conjecture is something which essentially amounts to the modularity of these Galois representations, provided they're odd, that they have complex conjugation has a certain behavior. And this was proved in many new cases. In fact, so it was known in cases of solvable image before by Hecke, Langlands tunnel, and so on. It was proved in many non-solvable cases, the so-called icosahedral image case, by notably Buzzer, Dickinson, Shepard-Barron, and Taylor around 2003. Then there's Serre's conjecture, which was also mentioned briefly in Andrew's lecture, where one considers instead representations of the Galois group with values in a finite field, still two-dimensional representations and still odd. And then this was conjectured by Serre that all such representations were modular, and it was somehow the philosophical underpinning of Shimura Taniyama implies Fermat. And this was proved or published at least around 2008 by Carré and Vincent-Berger, as Andrew also mentioned. The Fontaine-Mazur conjecture, which concerns now two-dimensional Galois representations with p-adic coefficients. And here one is interested not just in understanding the modularity, but also the more basic question of what are the p-adic representations that arise from Diophantine equations. It turns out that not all p-adic representations have this property, so one has to kind of have some conditions, surprisingly, it seems that the simplest route to showing that a Galois representation arises from a Diophantine equation is to show its modularity, and that's what led to progress on this Fontaine-Mazur conjecture arising from work of many people, including Colmez, Emerton, and Kizin around 2010. The Sato-Tate conjecture is a conjecture which was formulated by Sato and Tate, and it concerns the distribution of the numbers NP of E attached to an elliptic curve. And that was proved in large part and then gradually more and more generality by Clauzel, Harris, Shepard-Barron, and Taylor. And using again, the idea was to get a handle on the zeta function by proving an appropriate modularity lifting theorem. And then, one can consider also cases of modularity over more general number fields. The most natural case after the rational numbers are quadratic extensions of Q, or real quadratic fields, for example. And so one can consider the modularity because over real quadratic fields as a generalization of the Shimura-Taniyama conjecture, which was sort of implicit already, I think, in the original conjecture. And that's been proved quite recently, around 2015, by Nuno Freitas, Bao Lehong, and Samir Siksek. So in conclusion, I just wanted to explain that all these results that I quickly went through here are just examples. There are many more of the rich intellectual legacy of Wiles' proof. And, there's still many, many open problems in Langlands Program. It's very far from being solved. And so in some sense, the Wiles revolution growing out of exploiting these modularity lifting theorems is still far from over, and it's still very much of a lively, active subject. So having spent a lot of time talking about the legacy of Wiles' proof, I also want to maybe conclude with the remark that I think Andrew Wiles is the youngest of the Abel Prize winners so far. So the whole lecture shouldn't be only about legacy. So as I congratulate him on his Abel Prize, I also want to wish him many more decades of beautiful and influential mathematics. Thank you.